Yeah, so welcome back everybody. Now Yifeng will continue from yesterday's talk on recent advances on Beilinson-Bloch-Kato conjecture. Yeah.
Thank you very much. Okay, thank you. So this is the second talk of this, also the last talk of this lecture series. So let me first briefly recall what we've taught yesterday. So we first introduced the Beilinson-Bloch-Kato conjecture, starting from a Galois representation that as a polarized Galois representation, and then we define its L function and stated a conjecture relation between the order of the L function at 0 with the dimension or rank of the Selmer group. Okay, and we has explained that this is a generalization of the BSD conjecture. And then we went to a special case of the Rankin-Selberg product. We consider two elliptic curves and take their corresponding symmetric power and then take tensor product. Okay, and then we state our main theorem, which assuming certain conditions on the base field F and the two elliptic curves, we deduce that if the central value is non-vanishing, then the Selmer group is trivial for all but finitely many L. Then we explain a strategy of proving the vanishing of Selmer group following Holy-Wagen. Basically, the whole point is to construct, to find sufficiently many prime P, and then for each P, we can construct a special class called the CM, which will serve as an annihilator of the Selmer group. Okay. Then we make an assumption that we assume that the totally real subfield of F is not Q, and we also assume that F contains an imaginary quadratic field. That's only for simplification of the lecture. Then we introduce the key construction of this so-called level raising prime, and it satisfies 4 conditions. In particular, the second one is same as the level raising condition in the classical one, like studied by Ribet and other people. And the P3, P4, P1 is some genericity condition. Okay, only P2 is some exact condition. Then we explain what does this non-vanishing of L function imply. So using a recent result by Newton and Song, we attach 2 automorphic representations to the symmetric power of this elliptic curve as pi n and pi n plus 1 respectively. And they define 2 Satake homomorphism, which we denote by phi n. And then the Gan-Gross-Prasad conjecture, which is now a theorem, says that you can actually find 2 vectors fn and fn plus 1 in the corresponding eigenspace of the head character, such that the period sum is non-vanishing. Okay, and here this lambda n is a totally positive definite Hermitian lattice. It is important that it's a totally positive one. Okay, and then we fix the data lambda n and d throughout the remaining of the lecture, and then we started to construct the class CM. So the construction of CM uses some special kind of modular space. This modular space parameterizes quadruple. It's similar to the usual PEL type schema, right? But with a slight variation on the level structure. Okay, so it's a parameterized quadruple A, the abelian variety with CM, with OF action, with a polarization and the level structure. And we stated some initial property. Okay, we first defined 2 closed strata of the special fiber of the modular space, denoted as Mn circ and Mn bullet, defined by 2 conditions on the kernel of lambda. And then we also define several factorial morphisms from Mn to Mn plus 1, induced by the embedding of the Hermitian lattice. And we introduce an important notation called Sn circ, which is this double coset, which is a finite double coset. And they also have a functorial relation from the smaller one to the large one. And this Mn shared share the following properties. So first, it is projective, strictly semi-stable over the base ring, and is a pure relative dimension n-1. And the previously defined two closed strata are actually they separated the irreducible components of the special fiber into two parts. Each one is smooth, and their intersection is also smooth. Okay, and for the circ part, the MN circ, this part is relatively easy to study, and we claim that we prove that this is a projective bundle over the double coset, regarded as a zero-dimensional scheme over the base field. Okay, and we have this functorial diagram. And this intersection turns out to be a relatively simple hypersurface of this projective bundle, which is just the Fermat hypersurface. And finally, we explained that the generic fiber of Fmn can be identified of a Shimura variety associated to another unitary group defined by a certain nearby Hermitian space of the original Hermitian space given by the lattice. Okay, these are what we've done yesterday, and today we will continue. So far we have two things, right? On the one hand, we have the automorphic input, which give you a non-vanishing period sum. The second thing is some geometry. So how can one just relate them? I mean, one is functional theoretical, the other is arithmetic geometric. Okay, so what is the relation? So the relation, there's a name called explicit reciprocity law. So now I will explain. Okay, this is the key, the single most important key statement, technical statement of proof. For proof, in order to prove that, let me introduce slightly more restriction on the prime L. Also recall that our main theorem states for all but finitely many L. So we will exclude the finitely many L, gradually excluding them. So every time we will put more condition on L, and every time such condition will only exclude finitely many. Okay, so one more notation is the following. So for any positive integer m, we denote by m and m. Sorry, too many m. The kernel of the composite map is the composition of the Satake homomorphism phi n from Tn sigma to z, followed by the mod m map C to Z mod m. Okay. So here we need to use an important result by Karani-Schalter, and we show the following condition. We know that from their theorem, we know that for all but finitely many prime numbers L, they satisfying the following condition. So if you localize the cohomology of the generic fiber at the mod L, the maximal ideal of the Heck algebra defined by mod L Satake parameter of this automorphic representation. If you localize it, then it vanishes, except it is non-vanishing only when I is the middle degree. In other words, if I is not the middle degree, this localization is always zero. Okay, that's a highly non-trivial result of Karani-Schalter. So this holds for all but finitely many L. So in other words, from now on, we can just assume this condition L3. So recall that we already have L1, L2, right? L1 is elementary. It says that L does not divide sigma. Sigma is the primes where something is bad. Okay. L2 says that the joint Galois image of the two elliptic curves is the maximal possible one. Okay, that's L2. Now L3 is even more technical. It says that if you localize at the ML, it vanishes away from the middle degree. Okay. Okay. To introduce more notation, so we have two modular space Mn and Mn plus 1, and we take a fiber product which we call P. Again, P stands for product. Okay, P as this one, and similarly we define this P prime as the generic fiber of P, and this normal P as the special fiber of this curly P. Then we have the closed subscheme called M diag, which is the graph of rho m. By the way, rho m is this functorial morphism. Okay, so in particular, the graph of rho m is a closed subscheme of P. Okay, and similarly, we have a closed subscheme M prime dag for P prime and M diag for P. Okay, so now we take a prime L satisfying L3. And for every integer, positive integer M, there is a Abel-Jacobi map. The Abel-Jacobi map, because we have this condition, so H2n here vanishes. So it directly maps to the second layer, what's that? Second graded piece of the Hochschild cell spectral sequence of the cohomology. So it gives you a class in the first Galois cohomology of this étale cohomology of the geometric generic fiber, and divided by m to the L to the m. Okay, and this m L to the m is the product of the two ideals. Okay, any question? Okay, so we obtain a class here. Okay.
What was alpha?
Sorry, say that again.
What was alpha?
Alpha is a notation just.
Okay.
Okay, so alpha is Abel-Jacobi map, and we apply this map to this cycle, we get an element here. I mean, here you can just regard it as a notation. So we have a cycle, and then we have an induced class denoted by alpha, M prime dag, which is given by the Abel-Jacobi map. Okay, and the class Cm in step 3 will be a certain factor of this class. Okay, now, but so far you see quite different, right? The Cm should be in the H1F of some Galois representation coming from these two Ibid curves, this T and tensor, this T and tensor Tn plus 1. But here it's some cohomology of some scheme, some variety. So there has to be some hidden relation, which I will explain later. Now, in order to state this explicit reciprocity map, let me introduce one more notation. So record that this H1 thing, which was asked yesterday to clarify the definition. This H1 thing is the quotient of the whole H1 by the unramified subspace. So H1n subgroup H1n. So that's called H1 thing. So in particular, you have a natural quotient map from H1 to H1c. Okay, now you apply this partial P to the P component of this class. So you apply P component to this class, then apply partial P, you get an element in H1c Fp H2n minus 1, this whole Galois, this whole étale cohomology. Okay, so it's a slightly complicated. So we have a cohomology of some variety, then we apply the local Galois cohomology, then we take its singular quotient. So it's three steps. Okay, 3 steps. Now, the explicit reciprocity law gave you a formula computing this element. Okay. So here's a main technical theorem. Okay. It says the following: there exists a positive integer called L A0 A1 F n lambda n d. This depending only on the subscripts. Okay, only on the subscripts. In particular, this one does not depend on P. P is some prime we choose later. Okay, only on the subscripts, such that for every prime number L, at least this amount. Okay, we will make sure this condition will include L1 and L3. Okay, so this is included. And every positive integer n, if P, and P is the underlying prime of the inert place P, is a level raising prime with respect to Lm, L to the m. Then the following statements hold. The first one, this quotient this quotient of the étale cohomology of the modular space as a Galois representation of F with coefficients in C mod Lm is in fact isomorphic to a finite copy of TL tensor C mod Lm. So TL is the Galois representation, the lattice we started at the very beginning. Okay, so this quotient of the étale cohomology of some variety is actually just some copy of the Galois cohomology, of the Galois representation we start from. Okay, so this is the link between this variety with the original Galois representation we want to study. Second, there is a canonical isomorphism between the singular quotient at P of this étale cohomology with this tensor of two sets. Two C mod Lm modules. Okay, so this means the function C-valued functions on this Sn circ. This is that's a bisets of the definite unitary group. Okay, the one we always have. Okay, so here this one. Okay, and modulo the because this Heck algebra also acts on this space, modulo this M and L to the M, and here you also have the second copy of the rank M plus 1. Okay. And by the way, this canonicality implies that also they are Heck equivalent. Okay, for this one maybe fine. Okay, so there is a canonical isomorphism. The third one is the following. So there exists a constant gamma, depending only on the subscripts A0, A1, N, and P. It's not even on L. Okay, which is L adequately. So it's a rational number that is L adequately integer, such that under the natural pairing, so the quotient and the kernel have a pairing, right? So this one, the dual is this one. They have a natural dual pair to C mod Lm, basically just the tautological pair. Now, if you pair the previous constructed element, which is the element in this H1 thing, and by 2, which is also an element in this quotient, together with two functions Fn and Fn plus 1 from this isotypic subspace, what do you get? When you pair them, you do get a formula that is same as the period sum appearing in the Gan-Gross-Prasad conjecture up to gamma. However, this gamma doesn't really affect because it's an L-adequate integer. Okay, it doesn't affect the divisibility. Right? Okay, recall that the only thing we care about is the divisibility of the element of the image of this element in H1C. So this gamma does not affect the divisibility. Okay? So this is the formula which relates the Gan-Gross-Prasad conjecture with the arithmetic of this a diagonal cycle. Okay? This is a highly non-trivial relation. And this relation is called the explicit law, explicit reciprocity law. I don't know who, maybe Damon called this first, but today Damon called this first, maybe. And but they're in the Gross-Zagier case. So here is a higher dimensional analog of the classical one. Okay. So any question on the statement? So this is the key technical result. Maybe I'll give you some time to digest the content of this theorem. Okay. Okay, let me explain a little bit more. So why? So recall that our goal is to construct CM, right? CM such that its image on the H1 thing has bound. Please.
We can't hear you. Can you turn the microphone on?
Yes, it is on. Sorry, can you hear me now?
geometric level raising implicit in this statement?
Hold on. Can you hear me now? Someone's
Is geometric level raising implicit in this statement?
Yes. The geometrical level raising is already here. Okay.
And
Any other question?
In part A, how many copies are finite copy?
How many copies? You mean here? The number of copies is same as the rank here. Because the number of copy, each copy will give you one rank 1 here, right? So you can compute it here. Okay. So in particular, statement 1 only tells you, statement 1 could be trivial if this one is 0, right? 0 is of course a 0 copy of anything. Okay, but the 2 tells you it's not a trivial copy as long as the right hand side is non-trivial. Okay, right?
Yeah. Yes.
Okay, cool.
So sorry, maybe just the last question. So geometric level raising is something which holds in quite generality, but somehow like the part 3 is after combining it with some reciprocity, like a statement.
Sorry, I don't. Geometrical level raising is the consequence of this P2 here. P2, P3, P4, this 3 condition give you this 2. Okay, so 3 is basically a 1 step further of 2. You don't need a further condition for 3. So 2 tells you they are same, and 3 tells you how to compute. Okay, how to identify. 3 tells you how to identify a particular element here with the right hand side. Okay. Yeah, it's better to state them together. If I only tell you second part, it still give you nothing to how to really compute element here. Okay, so 2 and 3 they come together. There's an even more general statement for 3, but for our purpose, this one is enough. And this one is the one that exactly relate to the Gan-Gross-Prasad conjecture. Okay, so let me continue my remark. So recall that our goal is to construct CM whose image under in H1 thing FP has bounded divisibility. Okay, but from this formula, you see it is equal to some Gan-Gross-Prasad period sum multiplied by an L-adic integer. But this one a priori is not just in C mod LM. It's an integer. Okay, it's an integer. Where is that? Okay, it's an integer, right? So you can actually choose sufficiently large L such that the number here is L-adic integer. So in other words, for L large, you can even make this an L-adic integer, which means that this divisibility is 0. So of course it has bounded divisibility. Okay, so that's the whole point of this explicit reciprocity law. It gives you a transfer the information, the non-vanishing of the period sum to the bounded divisibility of the image in H1 thing of the diagonal cycle. Okay, so in the remaining time, I will explain how to prove this theorem. Okay, how to prove this theorem. So in particular, how to even relate these two things, right? This one is some complicated Galois cohomology of some eta cohomology of a unitary Schmor variety for the space V prime. But this is the quotient of some function space on V, on the unitary group of V. There are two different groups. How do they relate? Exactly. Okay, so I will explain this, in particular this one. So now in what follows, we take a prime L that is sufficiently large as here, and assume that P is a level raising prime with respect to L to the M for some M at least 1. Okay. Okay, so the goal, the key technique to compute H1 thing is to use the so-called potential map. This concept is developed by myself like 5 years ago when I studied a 3-dimensional case of this problem. And it turns out that this construction is very general to high dimension, and it solves many, in particular applies to this case as well. So what is this potential map? Okay. So first, we recall that we have this model P, right? This is the fiber product of Fmn and Mn plus 1. And each Mn and Mn plus 1 are semi-stable. But if you take a fiber product of semi-stable things, you don't get the semi-stable. There is a singularity here. However, in our case, one can resolve this singularity very easily. So we can just blow up this P. Okay, let me just base change it to the completion, because we only need it, because this theorem is a local statement at P. So in particular, we can take a completion at P. And we take a blow up of this completion along the closed subscheme, which is the circle part times the circle part. Okay, and we denote by Q prime as the generic fiber and the Q as the special fiber. And it's easy to show that this curly Q is again projective, strictly semi-stable scheme over OFP such that no 3 irreducible components of the special fiber have common intersection. So previously for yes, so this is a consequence of this blow up. Okay, let me introduce one more notation. So denoted by Q0 is the disjoint union of irreducible components of Q. And then we denote by Q1 the disjoint union of the intersection of 2 different irreducible components of Q. In particular, both Q0 and Q1 are smooth. Okay, Q1 is smooth, and you don't have Q2 anymore. You don't have Q2, Q3 anymore because no 3 irreducible components have common intersection. Okay. And we introduce an easy notation in what follows. So for a scheme X over the quotient field, which is a finite field, we put X bar as its geometric, it's a base change to the algebraic closure. And we denote by gamma the absolute Galois group of OF over P. Okay, this one is isomorphic to Fp squared because P has degree 1 over Q. Okay, this one is nothing but the Fp squared. Okay, so some notation. So for every integer r, we define this B upper RQ as the alternating pullback. So Q1, each component of Q1 is the closed subscheme of 2 components here, right? Because this is the intersection of members from here. So in particular, you can pull back. There is an alternating restriction map, same as the one in the weight spectral sequence. Okay, I denote by delta 0 upper star. And there is also an alternating JSON map from the Q1 to Q0. But for JSON map, you have to raise the degree by 2 and raise the twist by 1. Okay, and I denote the dual one by B lower RQ. This is the co-kernel of the JSON, and this one is the kernel of the restriction. Okay. Now, from definition, there is a natural map from the upper R to the lower R 2n minus R minus 1. Because I guess this one to this one. So the kernel, a subspace of this one to the quotient space of the same one. So you want R to be, you want R go to 2n minus 1 minus R. Okay. And I denote by B upper R upper 0 as the kernel of this tautological map, and the B lower 2n minus R minus 1 lower 0 as the co-kernel of this tautological map. And one can show that composite map, you first go restriction, then go JSON, actually factors through. So this one, B2M minus RQ0 is a quotient of this guy, and the BRQ upper 0 is the sub of this guy. So this composition actually factors through this quotient, then here, then sub here. Okay, that's an easy computation. Now let me denote by C lower r as the Galois fixed part. This is the Galois invariant part of the B lower r lower 0 here, and the C upper RQ is the gamma invariant quotient of B upper r upper 0. Okay, and in particular, we obtain a map from C to C2. Yes. So in particular, so this map, so we have this map, right? Then the C2M minus R is the sub of B2M minus R. So C2M minus R map to B2M minus R0, then map to BR upper 0, then map to quotient, which is the C upper RQ. Okay, so you get this map, and this is called the potential map. Okay, so I mean, if you haven't, like, this is some quite this is related to some construction in the so-called Gilles-Souret-Alakelov theory over non-Archimedean fields. And if you have some idea about that theory, then you can realize that this one is in fact a non-Archimedean analog of the potential map in this of a similar map. There is a similar map in the potential theory for Kähler manifold in this complex geometry. Okay, but this one is a non-Archimedean analog, and this is called this map, which constructed through this way, is called the potential map. Okay, any question on notation or steps here? I hope at least I explain how to construct it. Okay, it requires some time to digest, maybe. There's nothing complicated in the construction, but the key is that this map is, the whole point is to realize that this map is the important one. Okay, the steps are not complicated here, just usual cohomology computation. Okay, now let's state the relation between this potential map and the singular quotient. So proposition, there is a canonical isomorphism between the H1 thing FP of the étale cohomology when you localize at ML, okay, this ideal ML, with the co-kernel of the localization of the potential map. So when you take R to be N, you will find that here is C lower N and here is C upper N. And the co-kernel of this map, you localize at M and L, there are canonical isomorphism between them. Okay, and then moreover, under the above isomorphism, how to compute this the image of the diagonal cycle in the singular quotient? Okay, this guy is an element here. How to compute this guy as an element in this co-kernel? Okay, this is actually coincides with image of the cycle class of the strict transform of M diag. So recall that M diag is originally the diagonal cycle in P, right? Now Q0 is a blow up of CQ0 is a normalization of the blow up of P. Okay, Q0 is a blow up to each this P. So you can take strict transform of the diagonal in the original product P in Q0. Okay, And this cycle class can be regarded as element here. Okay. Then now this co-kernel admits a natural cover from Bn0 to its Galois quotient, invariant quotient, which is CNQ. Then the co-kernel here is, of course, a quotient of CNQ. So you can all the way map down the cycle class of the speed transform all the way down to the co-kernel. And that element coincides with the singular image of the diagonal cycle in the generic fiber under this singular quotient map here. Okay, so this is how you compute a particular cycle in this co-kernel of the potential map. Okay, any question on this statement? Does it make sense? Of course, the proof is another thing. So this moment, let's just make sure this makes sense. The statement makes sense. Okay. Let me know if you want me to go back to some notation. Okay, there's a slightly more complicated notation. Okay, so to further simplify the discussion of this lecture, we will just consider the case where n is even. Okay, recall that originally we just considered n plus 1, and could be even or could be odd. So for simplicity, from now on we will assume n is even. It's like a U2 times U3 or U4 times U5. Okay. So then we introduce a little bit more notation. So we write n as the twice of a natural number r, and we denote by sigma the blow-up morphism from Q to P, and we denote this P circ dot as the product of circ and the smaller one with circ and the larger one with dot. Okay, this is a very intuitive notation, and we also denote by Q circ dot as its strict transform under sigma. And similarly, we have a P circ circ, P dot circ, P dot dot. Okay, because for each Mn, you have two different kinds of strata. So you take product, you have 4 different kinds. We have a P circ circ, P dot circ, and a P dot dot, and their versions in Q. In particular, this Q0 is the disjoint union of Q circ circ, Q circ dot, not dot, bullet. Q bullet circ and the Q bullet bullet. Okay, so we now recall that recall this. We want to explain how can one get a relation between H1 thing and this space of functions on some definite unitary group. So in particular, we will now construct a map called nabla from the H2n of Q0 bar, okay, so by the way, H1 thing, we have already identified H1 thing as the co-kernel of some potential map. And this co-kernel is the quotient of, okay, it's some quotient of this guy. And now it is okay, but if you look at the definition of Bn, Bn is just the kernel of this H2n Q0 bar. Okay, so it's H2n. Hold on. Yeah. H2n Q0. So we will define a map from the whole space H2, the whole cohomology H2 and Q0 bar to the whole space of CL value functions on the 2 definite unitary, this quotient of the definite unitary group. And this map will turns out to factor through this quotient C and Q and induce an isomorphism when you take the quotient. Okay, so C and Q is a quotient of a subspace of here. So turns out that this one will flex to C and Q, and then you take a further quotient in the co-kernel, then you mod M to the L to the M. So it induces a map from here to this one mod M to the L to the M. And it turns out that this quotient, induced quotient map will be an isomorphism. And we are done combining this theorem. So we have separated this isomorphism into two steps. The first step is purely geometric, which is the relation between the singular quotient as the potential map. Then we identify this co-kernel of the potential map with certain function space on the definite unitary group. This is a special feature of unitary Shimura variety. Okay, and this one is very general. This one is even true for more general variety. But this one is very special for our particular modular space. Okay. So the remaining time, we will focus on the construction of this nabla. Okay, let's continue of the construction of nabla. So basic locus. So the construction of a nabla, to construct nabla, we will find many cycles containing Q0 that are actually indexed by this finite set for both n and n+1. Okay, it turns out that the union of those very special cycles we find is exactly the basic locus of Mn. That is the locus where this the p divisible group at p of this abelian group is a supersingular. Okay, so first let us recall the easy part. So we have mentioned that. So first, indeed, the whole easy part, which is Mn circ, is containing the basic locus. We also recall that it is a projective bundle over Sn bar and fits into the following diagram. So this is easy. We have related Mn circ to this Sn circ. And the close-up scheme Mn dagger of Mn circ is a Fermat hypersurface of degree p+1. Okay, that we have already mentioned even yesterday. Okay, but this is not enough. Recall that we have another part of the strata, which is Mn bullet. We can't just forget about Mn bullet because Q0, they have 4 pieces, right? You either have circ, bullet, bullet, circ, and bullet, bullet. And this property only takes care of the circ one. That tells you nothing about the remaining 3 pieces. And it is the bullet part that is the most mysterious and is the hardest to study. Okay. So how to study the bullet part? There are some even more sophisticated cycle sitting in the bullet part, which we now construct. To study the basic locus on the bullet part, we now fix an OF submodule. I call this lambda n bullet. It sits between original lambda n and p lambda n, such that the quotient of lambda n bullet by p lambda n, which is by definition is the subspace of lambda n over p lambda n, and this one is a Hermitian space of rank n over a finite field. Okay. By the way, we have assumed that from now on, n is the even one. So this is an even dimensional Hermitian space. And we require this quotient is a Lagrangian subspace, which has dimension half of n. Okay. And then we put the lambda n+1 bullet as the lambda n bullet plus a unit line. And for n, either n or n+1, we put Sn bullet as the double quotient, but we replace the original knd by kd bullet. Okay, and you just replace lambda n by lambda n bullet. We also put Sn dagger as the double quotient, but use knd dagger. And this knd dagger is just the intersection between knd and the knd bullet. And similar to row S circ, we have maps row S bullet and row S dagger. Okay, this functorial map from the smaller one to the larger one. Okay, any question? These are just notation. Okay, no, we haven't touched any real math yet. So just some notation to state the following construction. Okay. Okay, so what do we do? What do we do? We did the following thing. So we construct a commutative diagram as the follows. Okay, and here this row, what is this Bm? So this is a dimension has n minus 1. This one has dimension n. This one has dimension 0. This one has dimension 0. And we construct a diagram like this. So for each index n or n plus 1, we construct a correspondence between a 0-dimensional scheme and an n minus 1-dimensional scheme. And this Bn bullet to Sn bullet, this is a projective smooth morphism of dimension r. Recall that r is half of n. For example, when n is 4, this one has dimension 0, dimension 2, dimension 3, dimension 4, dimension 2, dimension 0. Okay, and this this B bullet to M bullet is a closed immersion when restricted to each connected component of the source. Okay, which means that if you take any point here and consider it's a fiber, then this fiber maps to Mn bullet as a closed immersion. Okay, so in other words, the Bm bullet is just this joint union of some cycles of dimension r inside this Mn bullet, and these cycles are indexed by this finite set Sn bullet. Okay, this is another interpretation of this diagram. And moreover, this row n bullet, this functorial map is also very easy. This is an isomorphism, locally an isomorphism. Okay, so here we have seriously used the simplified assumption that n is the even one. When n is the odd one, we have a similar relation, but much more complicated to state. So that's why we make that not much more, but slightly more, not slightly, I mean, just more technical to state. But there is a similar phenomenon where n is the ordered member. Okay. But for simplicity, let's just assume n is even. Okay, there are furthermore properties. The fibers of the morphism from Bm bullet to Sn bullet are certain Beilinson-Bloch-Kato varieties. So what are they? For example, when n is 2, the fibers should be dimension 1, right? Because the dimension is half of n. Those are just isomorphic to P1. When n is 4, those should be some Beilinson-Bloch-Kato surface. And the fibers are up to purely inseparable morphisms. They are blow-ups of the Fermat surface along all OF mod P points. The number of, what are the number? The number should be P plus 1 times P cube plus 1. Okay, so you blow up those points, rational points, and the fibers are essentially up to purely inseparable morphism, just those blobs. Okay. And we also show that, I mean, one can show that the union of the whole circ part and the image of the hold on. Yeah. So there's a typo. It should be this B, not the Roman B. Okay. The union of the circ part and the image of the B bullet should exactly be the basic locus of Mn. Okay, and how do they intersect? So the Bn bullet is something here, and Mn circ is the other part. So how do these two parts intersect with each other? So we have the intersection between Mn circ and the Bn bullet are characterized by the following diagram. We actually have the following diagram. So originally Mn circ lives over Sn circ, and the Bn bullet lives over Sn bullet. But if you take the intersection in over Mn, this map actually factors through the subspace called Sn dagger. So what is Sn dagger? It just remind you that Sn dagger is this quotient. Because this one is the intersection of these two different level group, so Sn dagger maps to both Sn circ and Sn bullet. Okay, in particular, Sn dagger is a subset of Sn circ and Sn bullet. So our claim is that when you take intersection, they factor through this subset. In other words, a component here intersect with a component here if and only if the elements that index them are linked by the correspondence defined by Sn dagger. Okay, so as you can see, the hack operator already appears here. Okay. So in the category of OF over P schemes, in which the fibers of the left morphism, and also the fibers here are quite easy. This is a dimension R, and this one is the intersection should be a hypersurface inside the Bn bullet. And the Bn bullet has dimension R. And this hypersurface turns out just to be isomorphic to the projective space of dimension R-1. Okay, and you can see what are the intersection here. In the example when n is 4, the intersection are exactly the exceptional divisor. The exceptional divisors are P1. They are exactly the exceptional divisors in this Deligne-Stieg surface. Okay. Any question for this picture? Okay, now we remember that our goal is to construct a map from the cohomology of Q0 to this space of functions on the definite unitary group. Okay, and this map is the appropriate sum of 4 maps. We now define 4 maps, which we call incidence maps. And the final one nabla will be the sum of these 4 maps. Okay, these 4 maps are quite technical. So quite technical in terms of notation, but the geometry is not that complicated. Let me first introduce first one. I call it circ dagger. Okay, the source is the cohomology of Q bullet, circ bullet. The first step, we first push down along this is the JSON map along the blow up. We first push down to the cohomology of P circ dot. Then by the coordinate formula, this is same as the, okay, I'm cheating a little bit. Everything should be after localization. Okay, so by coordinate formula, this one is same as the H2R of the Mn circ times H2R MM bullet. Okay, so maybe I should, instead of write equal, I should write a arrow here if we don't take localization. Then you take a restriction. This one remains, and you take a restriction from bullet to the intersection of bullet and circ. You go to the dagger. Okay, then this is like you first pull back from bullet to circ, then you push in to push forward to dagger to the circ. But this step, you need to raise the second one degree by 2 and twist by 1. Okay, now both Mn circ and Mn plus 1 circ are projective spaces, projective bundles. So the cohomology are just all same in even degree. So you can raise the degree using Lefschetz hyperplane, any hyperplane. Then you go to the top degree, which is 2n minus 1, and here is 2n. Now you push down by JSON map to the base. The base is just the 0-dimensional scheme parameterized by the double coset. Okay, you get CL Sn circ to CL Sn plus 1 circ. This is the first one. This one is the easy one. Okay, the remaining three are even more sophisticated. And you see from first one that it only uses, essentially only uses mn circ. It doesn't really use too much on mn dot or bullet, but the remaining three will use the bullet. Okay. For example, now we introduce the second one, which is the in circ bullet. This one also from the Q circ bullet. You first push down along the blow up to P circ bullet, then you use Cooney decomposition to the mn circ and mn plus 1 bullet. Then you take a restriction for the second one, you restrict the second one to the B part, okay, to the B bullet. Now you use the hyperplane again for the first one, you raise degree to the top to n minus 1, and the second you do not change it. However, 2r is already the top degree, the dimension of this B bullet. Okay, this B bullet has dimension r. Okay, so here is already top dimension. Now you can, because it's top dimension, this cohomology is same as the space of functions on the base. The base is 0 dimensional. Okay, so you get JSON map you do to this space. So you see there's a Sn circ, Sn plus 1 circ, but now there's an Sn plus 1 bullet here. Then we have a similar one, which called the bullet dagger, which is from Q bullet bullet. Okay, the third one is similar to the first one. So I will not, okay, not how to say, sorry. The third one is kind of a combination of the first one and the second one. So I will not explain in more details, but you can, I will send you slides and you can try to figure out how it goes by yourself. Because the key idea has already appeared in the construction of the first two morphisms. So let me just quickly say that the third one is from bullet bullet to the Sn bullet times Sn plus 1 circ. And the last one is the bullet circ, sorry, yeah. The last one is from the bullet bullet to the Sn bullet times Sn plus 1 bullet. Okay. By the way, so our goal is to turn everything to this space, not to the bullet one. But how to, so there's a relation between circ and the bullet given by this Heck correspondence for the definite permission, definite unitary group. So for any n is n either or n plus 1, this correspondence of the finite sets will give rise to two so-called transpose maps. It's either from the function space on circ to the function space on bullet, you pull back, then push forward. Or go to the other way, you pull back from bullet, then push forward to circ. Okay, according to the domain. Both of them I will denote by Tn. Okay, you just tell by the context. So now we now define nabla to be the sum of the following four maps. The first one is the ins circ dagger, and you apply both sides, you apply twice the transpose map. So when you apply twice the transpose map, you go back to circ. Okay, so the range of this map is circ times circ. And now this circ bullet, the in circ bullet has image here, so you need to apply transpose map twice here and the transpose map just once here. So the second one is transpose map twice here, once here, but you need to multiply a weight here. And the third one is the bullet circ. So you transpose once here, transpose twice here, and there's a weight here. The last one is bullet bullet. So you both transpose, you apply transpose map once on both index, and you have a weight which is p plus 1 to the cube. Okay, proposition. The map nabla defined above factor through C and Q and induce an isomorphism as we have claimed. Okay, so now you want to ask how do we figure out this technical map? Okay, that's a long story. That's there is a heuristic way to figure out. It's not by guess. Okay, we just don't guess it. There is a very complicated mechanism behind it to force us to define nabla in this way. Okay, as far as I know, there's no other way to make it work. This is essentially the only way to make this true. Okay, so I will just stop here. Okay, thank you.
Yeah, questions, comments?
Steps. I use work of Shao Zhu, geometric Satak.
Oh yes, it use. Oh, sorry. There is a chat. Okay. Yeah, there. Yes, the use of that is a hidden. For example, it's hidden. Okay, it's hidden at many places. Okay, I will say that way. With that result, for example, it's hidden. First, it's hidden here. Okay, the fact that gamma is invertible is already some consequence of this intersection number, and also the level raising condition. The level raising condition, why it is still works for symmetric power of Elliptic curve, also a consequence of the intersection number formula of Shao and Zhu. Yeah.
So in this explicit reciprocity law, let's say if you take some kind of periodic Abel-Jacobi, then do you expect on the right-hand side some periodic L function kind of stuff here?
Okay. Okay, this is some sort of L-adical one. If you periodic one, yes, I think so. That the expectation is like that. There should be also some periodic explicit reciprocity law related to some periodic special value, special periodic function. That's right. Yeah. Yeah. Actually, we are currently doing some follow-up work of this one, which will apply to some anti-cyclotomic Iwasawa theory. And there is another similar reciprocity law will exactly relate to your question. Yeah.
And like your main result, I mean, is it possible to generalize this to more general GLN cross GLN plus 1?
Okay. So you mean the very first result, right? This one? Oh, no. Okay, this one, right?
Yes, yeah.
Yes, we actually have, so in our paper, we have two versions of theorem. The first one is this one, and the second one is for abstract automorphic representation. But we have some local condition. Not all of them, but some mild local condition. For example, like a Steinberg at one place, something like that. Yeah, or a super singular at one place, something like that. Yeah. There is a version of theorem for abstract automorphic representation with certain local restrictions. Yes.
Any more questions, comments? If not, let's thank Yifeng again.
Thank you.